In this video, we are going to be considering the Maxwell boundary conditions which govern how electromagnetic waves propagate once they strike upon an interface between two different media. Let's go ahead and jump right into it. Okay, let's go. The Maxwell boundary conditions. How do we tackle this? Well, first of all, let's go ahead and write out Maxwell's equations. And we are going to write out the integral form of Maxwell's equations, because this is going to be how we are generally going to approach the boundary condition problem, is by generally taking a integral over either a surface or a volume. So here they are. Here are our four Maxwell's equations in integral form, and for each of these Maxwell equations we are going to get one boundary condition. And as you notice, there are four terms in the equations which are field terms. There is the D, B, E and H terms, and we want to find out what happens to each of these four fields at the boundary. So let's go ahead and draw out the interface that we are considering. So this is going to be the boundary between our interface, and I'm going to say that everything above the boundary will have a refractive index of n1. And remember, we use the refractive index, which is the ratio between the speed of light in a vacuum and the speed of light in a medium, to quantify how much light slows down within a particular medium. And this medium underneath is going to be of a refractive index n2. And so what is going to happen to any incident radiation? Let's say we have a ray of light that is traveling in this direction at a certain angle to the normal, which I'll draw out like this. What is going to happen to our incident ray? Well, as hopefully you guys probably know, some of the ray will get reflected back right here. And of course, we know that the angle in which it gets reflected back, which I will call theta r, is exactly the same as the incident angle right here, which I'll call theta I right here. So this is our reflected ray. But we're also going to have a refracted ray. Now, because reflection and refraction start with the same letter, we normally use the term transmitted right here. So we say that the ray that is transmitted through the material is actually the ray that refracts inwards. And of course, we actually know that the angle of refraction is not the same as the angle of incidence. And the way in which you work out the angle of refraction, or the angle of transmission in our case, is that you use Snell's law. We will be deriving Snell's law later on, but hopefully you guys know a little bit about Snell's law already. So this is our situation. Now, what is light for our purposes? Obviously light is a quantum mechanical thing, but we are still in classical regimes, so we are going to be considering light as a propagating electromagnetic wave. Now, as we showed before, a propagating wave right here will have an electric field right here, which is at right angles to the direction of propagation. So if this is our z-axis right here, then we have our electric field, which is along the x-axis right here, and it's oscillating up and down in a direction that's perpendicular to the direction of propagation. And we also have a magnetic field which is oscillating to both the electric field and the direction of propagation. But the magnetic field, we said, was actually a factor of c, where c is the speed of light, times smaller than the electric field right here. So we say that B, the magnitude of B, is equal to E divided by C. But of course, this right here is the speed of light in a vacuum, and for our cases, we're actually considering the speed of light in a material, or a dielectric in this case. So we actually write that it's equal to E divided by V, where the velocity is equal to the speed of light. And of course, we can use the definition that the refractive index is equal to C divided by V to say that B is equal to E times N divided by C right here. And this is an equation we will be using a little bit later on. But for now, let's return to our ray diagram. Now, I'm going to redraw this ray diagram, and for now, we're just going to say that the electric field vector is going to point in this direction right here. Now, of course, the direction is actually quite a complicated thing in and of itself, and we will come on to how the direction affects things later on in the video. But for now, I'm just going to consider any electric field that's just in this direction for the sake of argument. So this is our E vector. Well, what we can do is we can actually resolve the electric field into two different components. We can resolve it into a normal component, where of course the normal is parallel to this surface normal right here. So we can say that this is En, which is the normal component. And we can also resolve it into a tangential component right here, where of course the tangential component is obviously parallel to the boundary right here, the direction of the boundary along here. So we can resolve any electric field into two different components right here. Now, I'm just going to add the subscript 1 onto the ends of these electric fields because, of course, this is in medium 1. And we can do exactly the same thing in medium 2. So we have our electric field, which is in medium 2, which we are going to split into a normal component and a tangential component. So let's go ahead and apply Maxwell's equations, and let's go ahead and start with Maxwell's first equation, which says that the closed integral of d dot ds is equal to the integral of rho f, where rho is the free charge, over the volume. Now, what are we considering? We're taking two different dielectric media. One is N1 and another is N2, where of course electromagnetic waves can propagate. We're not considering any metals. And so, given we're in a dielectric media, and we've already accounted for the fact that there are bound charges using this D term right here, then what is the right-hand side of this equation? What is the free charge in the system? Well, the answer is 0. There is no free charge whatsoever in either of our media because we're not considering a metal. We're considering a material where electromagnetic waves can propagate. So we know that the closed loop integral of d dot ds is equal to 0 right here. So what should we choose for our surface right here, which is going to encapsulate a volume? Well, normally with these kinds of things, we like to choose a surface that reflects the symmetry of the situation. Now we have a flat plane right here, essentially. I've only drawn a line because it's in 2D, but if this was in 3D, this would just be a plane extending off to infinity right here. And so what do we do when we have a flat plane? Well, we actually use something that's called a pillbox. And a pillbox is essentially a cylinder, or you could actually use a square, but we're going to use a cylinder. It actually doesn't matter in this case, and you'll see why later. And this cylinder kind of straddles the surface right here. So this is our Gaussian surface that we have constructed. And as with all Gaussian surfaces, we are going to analyze what the flux is that's coming out of the surfaces of this cylinder right here. Now, we've actually drawn the E field in our two ways right here, but this equation right here actually wants us to consider the D field, the electric displacement field. But of course, we know that D is equal to epsilon times E right here, where of course epsilon is the permittivity. And you can actually also write that the epsilon is equal to the relative permittivity times the permittivity of free space right here. And we actually know that the relative permittivity for a material which is not ferromagnetic is equal to the square of the refractive index right here. Now, if you haven't seen this before, I recommend checking out my video on the microscopic oscillator model, in which I discuss how the relative permittivity is related to the refractive index. But hopefully you guys would have seen this before, in that the relative permittivity is equal to the square of the refractive index. So with that all said, I'm going to replace all the E's in this diagram with D's. So there we go. Now we can start thinking about what the flux is going out of the surfaces. So with a cylinder, we have three surfaces to consider. We have the top end, we have the bottom end, and of course the sides right here. Now I'm going to label the top end as having an area of A right here. And of course this is going to be the same on the bottom. And I'm also going to label this height of the cylinder in question as L right here. So what is the flux? Well, this closed integral is going to be the sum of the flux going out this end, the flux going out this end, and of course the flux going out the center. So what is this sum going to be? Well, we have this component of the vector right here pointing out of here. So we're going to get a positive flux from dN1 right here, multiplied by the area right here. So that's going to be our first contribution of this term right here. But we're also going to have a flux that is going in this direction from the bottom. And so because it's going up from the bottom into the surface, then this will actually be a minus term. So for the dN2 right here. So those are our first two terms. What about the flux going out the sides? Well, of course, we have dt1 and dt2 right here, and they are both going to be going out of sort of this side of the cylinder. However, for reasons which will immediately become apparent, I'm actually just going to add on the rest of the flux that's going out of the sides as gamma right here. So this gamma term is all the flux that's coming out of the sides of this cylinder. And we said that the sum total of all of this sum is just going to be equal to 0 right here, because of course there is no free charge within this cylinder. Now, here comes the trick that we often like to use with the boundary conditions. It doesn't really matter how tall this cylinder is, because of course we're only interested in what's happening at the very surface right here. And so we are going to consider the limiting case where we have our boundary right here, but we have our pillbox just about straddling the surface between the two boundaries right here. So we literally have a case where this pillbox is infinitesimally narrow, but the area right here is still exactly the same. And the reason this doesn't change anything is because this pillbox is still encapsulating the boundary, and it's still encapsulating both fields at the boundary and is analyzing what is happening. So what's going to happen to our summation right here? Well, if we reduce the height of this cylinder, then there is not going to be any flux going out of the sides of this cylinder right here, which basically means that this gamma term is going to be equal to 0 because there is no flux. And so as the height of the cylinder tends towards 0, then we get the limiting case that dN1 times A minus the normal component of D in medium 2 times A is equal to 0. So that's what happens as L tends towards 0. And this will still have the same behavior of the electric displacement field. Now, of course, we can factor out a factor of A right here. Now, of course, the area A is definitely not equal to 0 because it's a size which we constructed. And that must mean that dN1 is simply equal to dN2 right here. And that is the first of the 4 Maxwell boundary conditions. And this is the boundary condition that regards the electric displacement field. And that basically is saying that the normal component, which is of course the component that's parallel to the normal axis, will transport across the boundary right here. So there we go, that is our first boundary condition. Now, I'm actually going to go and jump ahead to Maxwell's third equation right here. And the reason I'm doing that is because I want to consider all of the electric fields first before the magnetic fields right here. So Maxwell's third equation is this right here, where E and B are the electric fields kind of as normally known. So they're not the material independent fields, but Maxwell's third equation governs the E and B fields rather than the D and H fields right here. So let's go ahead and draw out our electric fields again. Now, this equation is slightly different because rather than having a Gaussian surface, this left-hand side concerns a closed line integral right here. And so that is going to equate to a loop rather than a surface. And the loop that we are going to construct is going to surround all of the electric fields right here. So here is our loop that is going to encapsulate all of the electric fields. And with this closed line integral, and you're constructing a loop, you go around the loop in a certain direction. And so we are going to choose to go around this loop in this direction. The actual direction doesn't really matter. You'll give or take a minus sign. However, it will all cancel out in the end. And this loop is rather complicated. We have lots of different directions within this loop. We're changing direction 4 times, being a quadrangle. But also we are evaluating the electric field within different media. See, this electric field is evaluated in a different medium as this electric field right here. So we're essentially going to get 6 components of this loop right here. And if we start from, say, this point arbitrarily, and then label the parts of our loop, we're going to get part 1 here, part 2, part 3, part 4, part 5, and part 6 right here. So let's go ahead and start evaluating it part by part and see what we're going to get. So the closed loop integral of E dot dl is equal to the sum of all of these different parts right here. Now we have an electric field that's normal right here, but that is both parallel to 1 and 3. But these two paths are equal in length, but opposite in direction. So therefore, part 1 of the loop and part 3 of the loop are essentially just going to cancel each other out exactly, because of course it's dot producted with E, the normal component, along both parts. So when we add together 1 and 3, we actually find that these cancel out to 0 and so don't contribute at all to anything. And the exact same thing is going to happen in the second medium with parts 4 and 6. So when we add together parts 4 and 6, of course both parts are parallel to EN2, but they are equal in magnitude and opposite in direction, and so therefore they are going to cancel each other out. So parts 4 and 6 are going to cancel. And so what are we left with? Well, we're only left with part 2 and part 5, and those are the tangential components of the electric field. And so we actually find that only the tangential components of the field contribute to this closed line integral and are non-zero. So let's go ahead and write out these. So this is going to be the electric field that's tangential in medium 1. And if we just, again, arbitrarily say that this length right here is L, this is going to be multiplied by L right here. It doesn't actually matter what we call this L because it will go pretty soon anyway. And this is going to be added to this part right here. But of course now, because we have the tangential component in the opposite direction to our line integral, this is going to equal a minus term right here. And so therefore we're going to have minus ET2 times that same length L. Now we're going to do the exact same trick yet again, and we are going to shrink our loop essentially along the vertical axis or the normal axis to essentially we have a loop that literally, again, just straddles the boundary right here. So we have a loop that goes around here, but it's now been shrunk. And we can see that the area in which this loop encapsulates is going to tend towards 0 right here. So if the area of this loop tends towards 0, then what's going to happen to our B.ds term? Well, that's just going to tend towards 0 because, of course, there's no flux when we integrate over the surface, in quotes, which has now essentially become a one-dimensional object. So therefore, in a limiting case, the right-hand side tends towards 0. And so this sum right here, in a manner very similar to the Gaussian case, is going to be equal to 0. And so let's just write that out. So as we did before, we can just essentially get rid of the L because it's common to both terms. And therefore we arrive at our second boundary condition regarding the electric field, which technically comes from Maxwell's third equation. And that is essentially saying that the tangential component of the electric field is the same across both boundaries right here. So this was slightly different to, of course, the previous result, where of course we got that the normal component of the D field was the same in both media. Now we're getting that the tangential component of the electric field is the same in both media. So this is a very different case, and as we'll see a little bit later on, this will have its own ramifications. But let's go ahead and move on to the next one. For our next equation, we're going to take Maxwell's second equation right here, which is going to concern the magnetic field right here, B. And this is the magnetic field B rather than the magnetic intensity H. So this is going to be for this term, and we know that because there's no magnetic monopoles, the right-hand side always has to equal 0. The total magnetic flux going out of a given surface must be 0. The net flux is 0. So let's go ahead and redraw our diagram, but only this time with the magnetic field. So because of course we have a ds term, we have a Gaussian surface, and so therefore we are going to construct the pillbox much like we did in the first example. And this is going to be a cylinder, could be a square if we wanted to, but it's easy, and as we saw, the area just cancels, that encapsulates the magnetic field vector right here. And well, this right-hand side of the term is always going to be equal to 0. So let's go ahead and sum up our different contributions for the flux that's going out of this surface. So if we say this area is A and this length right here is L, we get that the closed surface integral of B through the surface is equal to, well, we're going to get the flux coming out of this end, which is going to be Bn1 times the area, and that's going out, so it's going to be positive. But we're going to have flux that's going in this direction through the bottom, so they're going to get a minus Bn2 times the area. And then again, we're going to get all this flux that's coming out through the sides, which we don't really care about, but we just need to call it something, so let's just call it gamma. And this is going to be equal to 0 right here. And then we do the same trick where we let L shrink towards 0, and that essentially means that the pillbox is literally only just going to be a three-dimensional surface. It will kind of shrink towards a circle that's just straddling the boundary right here between the two media. And so we find that this gamma is therefore just going to tend towards 0. And so in the limiting cases, we're going to get Bn1 times B minus Bn2, all multiplied by the area, is equal to 0. And thereafter, we just get to our third boundary condition where we find that Bn1 is equal to Bn2 right here. So there is our result for the B field. We find that for the B field, the normal component of B transports across the boundary right here. So again, this is different to the electric field, but it's actually very similar to the electric displacement field for D right here. So only one more Maxwell equation to go and only one more Maxwell boundary condition to go. Let's go ahead and do this one. So here is our fourth equation. And the first thing to notice is this term right here. This is the integral of the current over the surface right here. Now, what are we considering? Well, yet again, we're considering a dielectric media, two dielectric media. What's the current going to be? Well, it's going to be 0. There's not going to be any current flowing. We're not considering any current flowing. So that term can essentially just disappear. And so we get this simplified version right here, where this relates the H field and the D field right here. So what do we have on the right hand side? Well, we have H dot dl. So in a way that's very similar to the Maxwell's third equation, which is of course Faraday-Lenz law, we can essentially go ahead and construct a loop right here that encapsulates both the fields on either side. And so in this example, we're going to be considering the H fields right here. So there we go. Those are all of our vectors with their components right here. And so, like we did with Maxwell's third equation, we are going to break apart our loop into 6 components right here. So we get this part right here, this part right here, and all of the rest of them going around our closed loop. And so let's go ahead and, just like we did, evaluate the total closed loop integral of h dot dl. So we're just going to write out these numbers right here. But yet again, we notice that we're essentially doing exactly the same thing. hn1 along this path is going to multiply together, but then will be exactly cancelled out by this part of the integral right here. So we're going to find that 1 and 3 cancel out, and we're going to find that 4 and 6 cancel out for the exact same reasons, because they're essentially anti-parallel with each other. And so we find that we only get the second part and the fifth part that actually contribute anything, which is the 2 tangential components of the H field. And this is equal to the time derivative of the electric displacement field over the area right here. So what are 2 and 5? Well, this is just going to be ht1 times L, if again this length right here is L. And that's going to be subtracted from, because of course these two are anti-parallel, ht2 times L yet again, right here. And that's going to be equal to the right-hand side. But as I'm sure you're going to guess what we're going to do, we're going to shrink this loop so that it only just encloses the boundary right here. And that essentially means that this ds right here, this surface, essentially becomes a line, a one-dimensional object, and so there's therefore not going to be any surface right here. So if there's no surface, then this is going to be 0 right here. And therefore we find that if we just delete the L's right here, we can get that the tangential component of the H field in medium 1 is equal to the tangential component of the H field in medium 2 right here. So there we go. We have our fourth and final boundary condition, which essentially says that it's the tangential component of the H field that transports across the boundary. So there we go. We have these 4 boundary conditions for each of these 4 fields right here. And so we find this quite interesting kind of symmetry going on almost. We find that for the D and B field, it's the normal components that transport across. Whereas for the E and the H field, we find that it's the tangential components that transport across. And so we can see sort of an interesting parallel between D and B right here and E and H right here. And that's quite interesting in a way, because D, of course, is the material independent field regarding the electric case, whereas H right here is the material independent field in the magnetic case. So I actually find it quite interesting that it's reversed between electric and magnetic fields. So you find that D is actually much more like B, and E is actually much more like H right here. So that's quite interesting. So I hope that was really helpful. In the next video, we are going to directly follow on from this, and we are going to directly apply these boundary conditions so that we can get the 4 Fresnel equations right here. And these equations are very important when it comes to many different parts of optics and sort of applied electromagnetism. So I hope that was helpful, and I will see you guys in the next video. Take care.